Okay, hello, testing sound. Hello. Checking if you can hear me. If there's anyone watching, please let me know in the chat. I see that in theory there are 2 people watching, so please let me know if everything is okay. If I can be heard. Okay, perfect. I see that Erav PL can hear me. That's great. Oh, and Real Cygnus is here as well. Hello. Perfect. Okay. So that's cool. Yep. So, hello. Good morning. Good afternoon. I don't know. For me, it's afternoon. For those watching, maybe not. But hello. Okay. Sun is coming out. I'll just put the blinds down a bit. Okay. Yeah, that didn't help much from what I can see. It's still bright. But yeah, it will be down like in an hour or so. But for now it's bright. Okay, so today I'm going to talk about the Coriolis effect again. I already put a few videos up about that with some simulations and stuff, so today I'll try to go a bit in depth about how Coriolis effect appears and what it is, and I'll try to cover a few misconceptions as well, because I have been discussing this stuff with some flat earthers recently, and I can see some things that are recurring. So I'll be trying to cover this stuff. So basically, yeah. So that's the plan. I'll try to say what Coriolis effect is, and then show some simulations I prepared. So the recent videos were with simulations in 2 dimensions, and I put up a trailer of 3-dimensional simulations. So I worked on that simulator a while, and it can show a few nice things. So I'll show that, but first things first, let's start with what I have planned for today. So first, reference frames. Okay, so the idea is that, yeah, I've heard a few flat earthers saying stuff like for Coriolis it's necessary to leave a non-inertial reference frame, or you need 2 reference frames. Actually, I have some screenshots of that. Let me show you. Just a moment. Yep. So here we have T. Brown in a comment under one of videos by Reichi recently, who said about the Coriolis effect, about a ball. I don't remember the context. It might have been a ball on a merry-go-round, and he's saying ball leaves non-inertial spinning reference frame and appears to deflect for observers still in the spinning reference frame. So it's clear that he thinks that there is such a thing as leaving a reference frame, and that there is such a thing as being in a reference frame, which are actually misconceptions, and I'll cover that in a moment. In another comment, he's saying that Coriolis effect is an apparent deflection caused by the person on the non-inertial spinning reference frame observing an object in the inertial reference frame. So again, something in a frame and something in a different frame, which doesn't really make sense if you know what reference frames are. And Sleeping Warrior also is saying stuff like this. The first requirement of Coriolis is to leave the rotating frame of reference. So again, leaving a frame of reference. And ironically, he's writing, again, you don't understand Coriolis, which, as we'll see, is, well, might be not quite correct. And yeah, he thinks he understands Coriolis, and that's kind of the problem here. And also he wrote something like, Coriolis is caused by a failure to conserve the momentum of an accelerating body, which actually is a bit of a word salad. But yeah, so let's get down to business. So what are reference frames first? So basically reference probably, let me just check. Yeah, okay, so I have 4 viewers now, that's nice. But yeah, so probably if someone is watching me right now, chances are you're not a flat earther, so you probably know all this already. But maybe at least this will serve as something to refer flat earthers to. Or maybe someone from the flat earth community will watch this at some point. That would be nice. I don't really expect many of them watching stuff like this, because as far as I know they are not really into watching debunkers, but maybe, just maybe. Anyway, so Piotr R is saying it's not true, I am a flat earther. Okay, that's cool. Okay, so the thing is, reference frame. So why is it nonsense to say that something is leaving a reference frame, or that an observer is in one reference frame and the object is in another? Well, a reference frame is just a coordinate system that is somehow tied to some reference points in reality. So let's say we have some, I don't know, some situation, and we have some kind of a rock here on the ground. So we are, I don't know, here is a house, let's say. Like here's a tree. I don't know, here is a person. Well, it doesn't matter. So for example, we can say that this rock will be the origin of our coordinate system. A point right under this rock is the origin, and we say, let's say it's 0, 0, 0. Okay, so we have to, okay, so that defined one point, but we still have no idea how to count the coordinates, so in which axis is in which direction. So let's say we say that this 3 point under this tree is 1, 0, 0. So now we know that the x-axis of our coordinate system is this way. And so let's say we have both the axis, and we already have a scale of distance on this axis, because now the distance between the rock and the tree became a unit distance in our reference frame. If we wanted to use some other units than this particular distance, we could measure this distance, and let's say it was 10 meters. So we can say that the point under the tree is 10, 0, 0, and now we measure the units on the axis in meters. Okay, so we defined one axis. So let's say the other two axes are defined like this. So the z-axis will be vertical, and the y-axis will just be perpendicular to these two, and let's say in this direction. So this will be the y-axis. And now we have a reference frame. That's already a coordinate system. We know which directions are in which axes are in which directions, and we know how to measure distances along these axes. So let's say, for example, this person is, I don't know, 5 meters along these axes, so it's 5 meters here, and let's say it's 3 meters this way, and so the coordinates of this person right now are 5, 3, 0, because they are on the ground. But for example, the top of the roof of this house can be some other point, and let's say it's again 5 meters this way, and it's, I don't know, 10 meters this way, and it's, for example, 4 meters up. So now this point becomes -5, 10, 4. Basically, this way we define the reference frame. We can assign coordinates to any point anywhere, and that's pretty much the point of a reference frame, to translate real life locations, real life positions into numbers, into coordinates. Okay, but that's just one possibility of a reference frame. So for example, if I don't know, if it was if we were on a merry-go-round, let's say, it might be more convenient to define. Okay, so let's say that this is not just a person here. Just a moment. So let's say this isn't just a person, but that in this point there is actually a merry-go-round. So we have a merry-go-round here, which has some handlebars here, and we have a person on this merry-go-round. So it might make sense. It might make sense for the person of this merry-go-round to define the axis of their coordinate system in a different way. So for example, let's draw it on a separate page because this is getting cluttered. So for example, if we have this merry-go-round and we have a handlebar here, and we have a handlebar here, and a handlebar here, and okay, I'm really bad at drawing, so you'll have to forgive me. Oh, I see a few other people. So I see Xman777. Hello, and I see CrowXE. Hey, nice to see you here. Okay, and we have a person on this merry-go-round. So for example, let's say this person marked the handlebars in some way. So let's say this is handlebar number 1, this is number 2, and this is number 3, and this is number 4. And this person decided that, okay, my x-axis will be, I'll define the center of the roundabout to be 0, 0, 0, and my x-axis will be along the handlebar number 1. So this is my x, and this will be my y, and my z will be again vertical. And so if this roundabout is spinning, then it means that, well, at some point in time this x will be the same as the x-axis we defined before, which is between a rock and a tree. But after some time this will rotate and the x-axis here will be pointing in a different way. So for example, let's say that we need to add time to the picture. So let's say that at time equals 0, these axes were parallel. Okay, so the tree here was at 10, 0, 0, and the center of this roundabout was at 5, 3, 0, right? So, for example, if we tried to calculate what the coordinates of the tree are in this coordinate system, then we'll see that, okay, it's 3 meters along the y-axis to the negative side, and it's 5 meters along the x-axis. So the coordinates of the tree at time equals 0 will be 5 minus 3, 0, right? We need to move 5 units along x, 3 units in the direction of negative y, and 0 in the z direction. And the coordinates of this rock would be minus 5, minus 3, 0. But let's say that at time equals, I don't know, 2 seconds, this rotated so that the x-axis is now pointed here and y-axis is now pointed here. So at this point, we need to move 5 meters along the negative y-axis, and we need to move 3 meters along the negative x-axis, so the coordinates became minus 3, minus 5, 0, right? They started changing. So in this reference frame, because this is another reference frame, in this reference frame the tree is moving because its coordinates are changing. That's basically what we mean by something is moving. In our reference frame, when we introduced some coordinates, if the coordinates are changing, then this is moving. If the coordinates are not changing, then this is not moving. And this is also why motion is relative. I mean, if something is moving or not depends on how we define the coordinate system. If we define the coordinate system so that the tree has constant coordinates, it's not moving because, well, the coordinates aren't changing. But if we define it differently and the coordinates will be changing, well, then it's moving. And that's pretty much it. So actually, in this rotating reference frame, if we looked at it, after time equals 4 seconds, then this will reverse once again, and we would get something like, we would need to move 3 meters along y-axis, and we would need to move 5 meters, so we would have minus 5, 3, 0. And in between, we could calculate, so in between it would be at 45 degrees angles. And I don't really want to calculate this right now because I have too much to say. I will leave this as the exercise to the viewer. Anyway, So yeah, so my point was that, yeah, something can be moving in one reference frame and not moving in another. And let's also note here that I'm not saying that the tree is in the reference frame of the rock, let's say, or it is in the reference frame of the person on the roundabout. That doesn't make sense. It is in both at the same time. It can be described in both. So reference frames aren't something you are in. It's just a frame of reference. It's a framework for describing positions of stuff and positions, velocities, accelerations, basically. It's a framework for describing motion, and it's not something that is associated with the object. So it's not like the tree is in one reference frame and the person is in another. No. We can describe the position of both the person and the tree in both reference frames, and actually we could introduce infinitely many reference frames. There might be, I don't know, there might be a plane flying overhead. So let me just erase this part. So there could be a plane here flying, and it can be flying at, I don't know, 200 meters per second. So it was, for example, in a point, I don't know, minus 100 and, I don't know, 50, and at an altitude of, I don't know, let's say 5 kilometers, right? So let's say it was at this point at time equals 0, and then at time equals, I don't know, 1 second, it will be 200 meters down the line, right? So it will be plus 150 and 5,000. Right? So this plane is moving, and if we introduced a reference frame that has like X, Y, Z here, then it would mean that, for example, in this reference frame, in time equals 0, the tree is at coordinates like 110 in the x-axis, minus 50 in the y-axis, and minus 5,000 in the z-axis. And in the next moment, the numbers are different. So that's another reference frame. But we don't even need the plane here. We can just define it using pure maths. So if we want to, we can say, okay, let's introduce a reference frame that has this origin at time equals 0, and that is moving with some velocity. So there doesn't even have to be a plane here. We can just abstractly define such a reference frame and say, okay, because for some reason we want to use such a frame, I don't know, we might have many different reasons to do that. So we say, okay, we just want origin is at this point at time equals 0, it is moving 200 meters per second in the x-axis, and the axes are parallel to the axis of the reference frame that we tied to the rock. Right? And tada, we have a reference frame. We can call this reference frame, I don't know, we can call it O prime, and this we can call O, and we have two reference frames, and we can consider what happens to the motion of stuff in these two reference frames, and this can be O prime prime, double prime, or I think it's called bis sometimes. Anyway, whatever. We can define it arbitrarily. We can have a reference frame that is both moving and rotating relative to a different reference frame. The possibilities are endless. They don't have to be tied to some physical objects, so we don't have to have some physical object at rest in a reference frame in order to have a reference frame. We can just define it abstractly. But of course we need to relate this in order to be able to describe positions from real world in this reference frame. We need to somehow relate it to real world objects. So even though the origin of this reference frame is not tied to any object, and the axes are not directly tied to any objects, well, indirectly they are, because we defined the axis in this reference frame as being parallel to the axis in this reference frame, and the axis in this reference frame were defined using objects like the rock and the tree. So indirectly the axes here are also defined using the rock and the tree, but yeah, indirectly. So we do this, and basically we say, okay, x is parallel, but it's in a different place, right? And we could write the exact equation that would relate coordinates in this reference frame to coordinates in this reference frame. And actually such equations are called transformation between reference frames, and this is what you might have heard of as there is a Galileo's transformation and there is Lorentz transformation in relativity. So this is basically it. These are equations how coordinates in one reference frame relate to coordinates in other reference frame. Okay, so yeah. So again, yeah, there is no being in a reference frame. Neither the rock, nor the tree, nor the person on the roundabout, nor the roundabout itself, nor a ball on the roundabout, which might have been here, for example, at some point, nor a plane that is flying overhead. Nothing is in a particular reference frame. It can be described in a reference frame. The motion of it can be described in a reference frame, but it isn't in. We can say that it is in a reference frame. And we can't also say that something leaves a reference frame, because how can you leave? First, how can you leave if you weren't in it in the first place? Because that doesn't make sense. And also, how can you leave a coordinate system? So, for example, what needs to happen to this ball here so that we can say that it left the coordinate system defined by this roundabout? It doesn't make sense. Where if this ball got launched into outer space and went to the moon still has some coordinates in this reference frame. So for example, if the moon is somewhere here, it's possible that it has coordinates like, yeah, I don't know, because if I want to have some realistic numbers, it might be a bit hard. But what is... Yeah, let's say approximately. I don't know, it's probably not really realistic, but so we could say something like 220 million in the x-axis, 220 million in the y-axis, and 220 million in the z-axis. And this is the moon at, let's say, time equals 0. Because I remind you, we measured the distances in meters, so hence why such huge numbers. And this, I think, if I didn't make any mistakes, this should roughly actually give the distance to the moon, which is somewhere close to the actual number. But yeah, that was like... those are just quick made-up numbers, and they might not make much sense. Anyway, so if we wanted to say that something is in some reference frame, well, in a sense the moon is in the reference frame of the roundabout, in that we can describe its coordinates using this reference frame. There is really nothing preventing us from that. It's not like it has no contact with a roundabout, so it's in a different reference frame. It's not like that. So this is the part that I would really, really love the flat earthers to start getting right, because this is the source of all misconceptions, because then they start talking about, okay, so the ball has to lose contact with the roundabout so that it is in a different reference frame, and then the roundabout starts rotating under the ball. It doesn't make sense. It never leaves a reference frame. It just might not be in contact with another object, okay, but this doesn't mean it somehow left a reference frame, because this very phrase doesn't make any sense. Okay, but I'm ranting about that right now, so maybe let's move on. Okay, so let me see what I wanted to say, and let me consult my notes. Okay, so that I said that already. Yeah, so again, let me just repeat that part, because I think it's really important, that a reference frame is only a framework for describing observations, for describing positions of objects, and it's not something associated with the observed object. So it's not... Yeah, okay, because I'll just start repeating myself again. I'm getting wound up by this. Okay, so let's go ahead and say what really is the Coriolis effect, but before we do that, we need to also define some other things. So, okay, so I said that, okay, for example, the tree isn't moving in the reference frame of the rock. So, yeah, we usually call the reference frames by what they are associated with. So when I'm saying the reference frame of the rock, I don't mean that something is, I don't know, in contact with the rock or attached to the rock. I just mean that I describe its position relative to this object. Okay, so if so I said that the tree isn't moving in the reference frame relative to the rock, but it is moving if we describe its position in the reference frame of the roundabout. So how do, and I pointed out that there are okay, let me write this again. So let's say at t equals 0. Okay, let's maybe use a simpler example, because if I do this, then we'll have some trouble in a moment. And I don't want to make this too complicated from the start. So let's say again we have this tree, this rock, and we have this tree. And again we have these axes here, x, y, z. And let's say there is a person walking by. So we have a person, and we introduce another reference frame relative to that person. So let's say this person is one meter from the rock in the y-axis. So let me maybe draw it. So let's say the person is here at time equals 0. So at time equals 0, their coordinates are 0, -1, 0. And the axis will be the same. So we aren't inventing anything new here. Only this person is now walking by. And let's say they are walking by at 1 meter per second. So it is in 0, -1, 0 in the, relative to this reference frame at t equals 0. Maybe let me draw that in a different part. Okay, so this should work. Oh, I just wanted to move it. Okay. Alright, so at t equals 1, this person will already be at 1, -1, 0. At t equals 2, they will be at 2, -1, 0, etc., etc. So we can now calculate the velocity of this person. And the velocity of this person is just, well, how much their position changed divided by the time. So the position changes in the first second by just 1, 0, 0. That's the change between this position and this position. And if we divide it by 1 second, then obviously we just get this back, and this is the average velocity during the first second. If we took a larger time span, so say after 10 seconds they will be at 10, -1, 0. Again, if we do the same math, we will just subtract, let's say t equals 10 from t equals 0 from t equals 10, and we have the difference of 10, 0, 0. And if we divide it by 10, we again get 1, 0, 0. So the velocity over the 10 seconds, the average velocity, is still just 1, 0, 0. And, well, that's to be expected because we just defined this person to be moving at a constant velocity. So nothing changes, and whatever time span we take, we will always get the same velocity, 1, 0, 0, because it's constant, so average is also constant over different periods. Okay, so that's cool. But also, if we look from the point of view of this person, yeah, Krawex is writing easy with the math, bro, yeah. Yeah, if someone doesn't get through this kind of math, I think we will really have trouble explaining more complicated stuff like the Coriolis effect. Okay. Yeah. So if we now try to do this relative to the person, we will find that, for example, the rock was this rock was at 0, 1, 0 at t equals 0, and then after 10 seconds the person moved 10 meters, so the rock is now 10 meters to the back, so it's at -10, 1, 0, and if we do the same calculation, we will get the velocity of the rock to be -1, 0, 0. So, yeah. And the velocity of the person in the reference frame related to the person is 0, because the person is always at 0, 0, 0 in this reference frame. So in this reference frame, the person is not moving, the rock is moving. In the reference frame relative to the rock is not moving, the person is moving. And we can say that one of these is somehow better than the other. Those are just two different ways of assigning coordinates to stuff, and both are equally valid. And that's kind of a big part of this is well, an important thing in physics, that you can define the coordinates pretty much any way you like, and the physics is still supposed to be valid and still is supposed to be working. But there is a caveat which we'll cover in a moment. So yeah, so basically we calculated velocity by checking how the position changes and dividing by time. If we do this with velocity, we will get the acceleration, and we will find out that the acceleration of anything here is 0. Well, anything. The acceleration of the rock and the tree and the person in both these reference frames are 0. Because, well, we only have, well, if it is constantly in a single place, position doesn't change, so the velocity is 0, velocity is constantly 0, so acceleration is also 0. And if velocity is constant, it doesn't change, so acceleration is also 0. And we didn't really introduce anything that would accelerate here. But if we, for example, wanted to go back to this situation and to describe the motion of the tree in the reference frame of the merry-go-round, then, okay, let's return to what we wrote before. So at t equals 0, the tree was at, what was it, 5 minus 3, 0. And now at t equals, okay, now at t equals 2 seconds, it was supposed to be minus 3 minus 5, 0. Oh, hello, Doranku. Greetings, and no worries, no need to apologize for being late. It's not like a class or something, nobody is obligated to be here on time. So, but thanks for coming, it's always nice to see that someone is watching. Okay, so now if we try to calculate the average velocity, we would get that the position of the tree changed in these 2 seconds by, it changed by minus 8 in the x-axis, so we get minus 8 here. It changed by, wait, do I write this correctly? From minus 5 to minus 3, I think it's correct. So from my, let me double check the numbers. 5 minus 3, okay. And then if we rotate it by 90 degrees, it switched to, it's a bit weird because I would, oh, okay, never mind. No, it's probably correct. Okay, so it's minus 8 in the x-axis, and it changed by plus 2 in the y-axis. No, wait, minus 2 because it's in this direction, and it changed by 0. And now we divide it by 2, and we get the average, and again average velocity over these 2 seconds to be minus 4 minus 1 0. But that's only average. If we tried calculating this in some kind of a shorter time span, for example 0.1 seconds, then I would have to actually calculate what the numbers would be, but they would be much different. So, okay, let's make something up. So, for example, if we take t equal 0.1 seconds, then this will be, okay, so I defined it to rotate by 90 degrees, 90 degrees every 2 seconds, so it means that a full rotation takes 8 seconds. So now it means that the angular speed is 2 pi divided by 8 seconds, so it's pi divided by 4. So now if we multiply it by 0.1 seconds, it means that it's rotated by pi divided by 40. So it rotates by this angle. And now we'll need to calculate this. Oh wait, why is it full screen? Let me just quickly increase the font size so that you see better what I'm showing. Okay. That's something that, well, that's a bit too much to calculate just on the fly. So we have angle equals pi divided by 40, and so x will be 5 times cosine of angle. And let me think if I should expect, I think I should, times sine of this angle. So that will be the x, no, okay, we're going the wrong direction. So this will be the x coordinate after this rotation, and the y coordinate will be minus 5 times cosine, times sine of angle, plus minus 3 times cosine of this angle, and this will be minus 3.4. So we have minus 338 and 475, let's say. So we have 475 and minus 338 and 0. And so if we now divide the differences, so if we now take the difference, so the difference is now minus 0.25, minus 0.38, 0, and if we divide it by 0.1, we will get the velocity to be minus 2.5, minus 3.8, 0. Okay. And if we decrease the time even more, then we would get a smaller change, and divided by this smaller time, it will again lead to some value, and actually the value here should be minus 3 pi divided by 4 and minus 5 pi divided by 4 and 0, and so that should be the proper value for the velocity, for the immediate velocity at time equals 0. Now, why this value? Basically, okay, how this can be calculated so that I'm not just spitting out magic numbers here. So this velocity of so we are rotating at an angular velocity which can be expressed as a vector, and it would have only the z coordinate, and the z coordinate will be pi divided by 4. As I said before, this is the angular velocity of this, and this is the position vector at t equals 0. And it so happens that, well, if it's here it's the tree is at rest in the reference frame of the rock, and it's the roundabout that is rotating, but from the point of the roundabout it's like tree is rotating relative to the roundabout. So basically, since we are rotating here, the tree is now doing this, and we can calculate this this velocity here by taking the cross product of the angular velocity and the position, well, with a minus sign in this under these circumstances, because how do I put this? So if we just did the cross product of omega times the position, we would get the velocity of the thing that is rotating at this angular speed. So in this regard, since this is the angular velocity of the roundabout, we would get that the points on the roundabout are moving with omega cross r in the frame of the rock But since now we're reversing the situation and we are asking how fast the objects that are not moving relative to the rock are moving relative to the roundabout, we have this minus because it's in the opposite direction. So now if we calculate this, this actually boils down to multiplying. So there is a pretty complex formula to multiply for a cross product of two arbitrary vectors, but for a vector that is just 0, 0, z times a vector that is just x, y, 0, it's quite simple because it's and now so I'm not lying to you. Let me think. So if something is here, it should be negative, so we should have minus zy here, and we should get zx here and 0. Okay, this way. So if we are now negating that, if this is omega and this is x and y, we have so minus omega cross r will be this but negated, so it will be omega times y minus omega times x, 0. And so this gives then omega times y is minus 3 times pi divided by 4 minus omega times x, so minus 5 pi divided by 4 and 0. And so if we enter these numbers, 3 times pi by 4 and 5 times pi by 4, so it's 2.36 and 3.93. Wait, here. So it's like minus 2.36 and minus 3.930. Yep. Okay. So we got, from this difference, we got something like minus 3.8 and minus 2.5, so fairly close. But yeah, the shorter time period we take, the closer we will get to this value actually. So this is called, yeah, I'm not sure if that's the proper term in English, immediate velocity, I believe. Let me, as opposed to average velocity. So it's just a velocity in a single point in time. Like, let me check if I got the term right. Instantaneous velocity. Oh, okay, so that's the proper term. Okay, so that would be the instantaneous velocity of the tree relative to the roundabout at t equals 0. But this will also keep changing, because as this roundabout is moving, the tree is moving in a circle. So basically, if we try this at a later point in time, we will get different numbers. So it also means that in the frame of reference of this roundabout, the tree is accelerating, because the velocity will be changing. So let me show you, let me just give you the proper numbers so that we are all on the same page here. So, okay, we had at t equals 0, we had coordinates 5, minus 3, 0. So, the equations will be like this. So for any time t, we will have x equal, let's call this x0 and y0. So this will be x0 times cosine of omega t plus y0 times sine of omega times t, and y will be minus x0 sine omega t plus y0 cosine omega t. So this is pretty much the calculation I did just a moment ago. I just substituted omega times t by pi divided by 40 and did this calculation here in Python. So that's pretty much it. So then the velocity. Now if you know calculus, then you can just take the time derivative of this, and you will see that the velocity in the x-coordinate will be minus omega x0 sine omega t plus omega y0 cosine omega t, and the velocity in the y-axis will be minus omega equals 0 cosine omega t minus omega y0 sine omega t. So when I calculated the velocity at t equals 0, then this part is the parts with the sign are 0, because sine of 0 is 0, cosine of 0 is 1. So we just got that the velocity in the x direction is omega times y0, and the velocity in the y direction is minus omega times x0, so that is correct. And then we have acceleration, and I wrote this in such a way that I now can't really... No, okay, this won't work really, because it doesn't cut this out. Okay, let me turn off the camera so that I have a bit more of the screen available. Okay, so now if we do the same thing and calculate the acceleration, we will get that the acceleration in the x direction is, and actually, okay, let me just write it out, and it will be minus omega squared x0 cosine omega t minus omega squared y0 sine omega times t, and in the y direction it will be omega squared x0 sine omega t minus omega squared y0 cosine omega t. And actually, if you compare this acceleration with this thing, then you will see that the x coordinate is minus omega squared x, and the y coordinate is just minus omega squared y, which is not really a coincidence. If you know a bit of physics, then you kind of probably see already that this looks something like a centripetal or centrifugal acceleration, and this is not a coincidence, but we'll get to that in a moment. But yeah, basically, if we now use this to calculate the acceleration, we will now figure out that the tree is actually accelerating in the reference frame of the roundabout. The tree is accelerating towards the roundabout with an acceleration of minus 5 omega squared 3 omega squared 0. And since omega was something like pi divided by 4, then this would be like pi squared divided by 16, but I didn't want to write it here. Anyway, the point is, if we analyze the motion of the tree in this reference frame, we will now come to the conclusion that the tree is accelerating towards the center of the roundabout. And it makes sense, because if you know anything about the motion of in a circle, basically from the point of the person on the roundabout, we are here, and we see that the tree started somewhere here, and it is going in circles around us. And if something is going in a circle, then it is experiencing an acceleration called the centripetal acceleration, and it is equal to omega squared times r, times the distance from the center, right? So yeah, so from the point of view of this reference frame, the tree is accelerating towards the person on the roundabout, even though if we are an observer outside the roundabout, we see the tree just standing there, not moving at all, and not accelerating. So we can see that the acceleration can somehow depend on the reference frame, and that's kind of the point behind the notion of an inertial reference frame and a non-inertial reference frame. So if something is accelerating, so how do I put this in a clear way? Okay, basically, Newton formulated his laws of motion, and he postulated that basically forces are something that causes an acceleration. So whenever you have a force acting on an object, then it undergoes an acceleration which is equal to this force divided by the mass of the object. But you can also reverse that and say that if an object is accelerating, then it is experiencing a force that is acting on this object. you can say that it is experiencing a force. So in this case, we would say that this tree is experiencing a force. So there is a force in this direction that is equal to mass of the tree times omega squared times r. Okay. So usually forces are caused by some kind of an interaction. So, for example, if I'm pushing something, I'm exerting a force. If, I don't know, I have two magnets, then they interact via the magnetic field and they are exerting a force on each other. So the forces that are caused by some kind of an interaction, we could say they are the real forces in a way. But sometimes we cannot really point to any specific source of a force, like in this example, for example, what really pulls the tree towards this person on the roundabout. There isn't really any interaction going on between this person and this tree, right? They aren't attracting each other, but we still see as if there was some kind of an attractive force on the tree. So here's where we make the distinction. So we say that there are these real forces caused by some interaction, and they are the forces that we can't really put our finger on it where they come from, and those we call inertial forces. And the point here is, so no, maybe I'm going at this from the wrong side. So let's put it the other way. If we look at the reference frame of the rock, again, we see that the tree is not moving, and we can also see that the forces on the tree, any forces that we can really point to, so there will be two such forces. There will be a force of gravity on the tree acting down, and there will be a force of reaction for the ground acting up, and the total force is 0, and the tree is not moving. And so we have Newton's first law that says that if all the forces acting on something are balanced, then it is not moving, or it is moving in a straight line. But as we saw, in the case of, if we look from the point of view of the roundabout, there aren't really any forces acting on the tree that we can point to. There is still gravity, and there is still the reaction force from the ground. So if we just tally up all the real forces, all the forces caused by some kind of interaction that we can point to, they seem to be summing to 0, but still the tree is accelerating. So basically we make the distinction that the frames of reference in which Newton's first law is satisfied, in which if there are no real, again, quote unquote, real forces acting on an object, then it is not accelerating. Such frames we call inertial. And if we have a frame of reference in which this is not true, in which all the forces, or all the quote unquote real forces, are in balance, and yet the object is still accelerating, but accelerating in the sense of the coordinates changing in this way, right? If we describe the position of the object in this reference frame, in this coordinate system, then if we calculate the velocity and the acceleration, it turns out that the acceleration is actually non-zero. Such frames we call non-inertial. But note that this definition has one point that is really a bit shady, and in that we kind of postulate that we can distinguish between, that we can point to all the real forces, right? So that we know all the interactions, and we can enumerate, and we can identify all the interactions and tally up all the forces caused by the interaction, and then check if the force that we got agrees with what we measure, right? So if we take all the forces, sum them up, calculate the acceleration of the object, and if it agrees with what we actually see in the reference frame, then we can say that, okay, this frame of reference is inertial. And if it doesn't, then we can say that this is non-inertial, but this assumes that we can enumerate all the interactions, that we know what all the possible interactions are, and that we can identify the forces related to it. So this is a bit of a weak point, and actually this is kind of the difference between Newtonian and Einsteinian gravity. in Newtonian gravity, gravity is just a force caused by an interaction, right? So we will just add a force of gravity like I did here to all the interactions that happen. And then we would say that this frame relative to the rock is inertial because when we summed all the forces, they were zero in total. The tree isn't accelerating, so this is an inertial frame of reference. But in general relativity, gravity isn't really considered a real force anymore. So in general relativity, we would erase this force here, and we would say, okay, so all the forces acting on the tree are not zero, because we have only just a single force acting upwards, and that is the push from the ground upwards. So the total is not zero, and yet the tree is not accelerating, which means that the frame of reference relative to this rock is non-inertial, and we have an inertial force acting down. And so gravity is kind of another inertial force in general relativity. Oh yeah, I think I didn't make it to that point, but basically in order to make the math check out, in non-inertial reference frames, we add something that we call basically this remnant, this acceleration that we cannot explain using the forces that come from some interactions, we call inertial forces. So in this case, we have gravity, we have the ground, the reaction of the ground, and in total they sum to zero, but we have a non-zero acceleration. So the net force is this, and basically the net force of all the quote-unquote real forces is zero. So basically this is something that is not explained by the forces caused by interactions, so we say that this bit is inertial. And actually in this case, okay, I will just if I said what it is now, I would probably confuse you. So I will go to this later, because you probably already, some of you at least probably already know that in rotating reference frame we have centrifugal force and we have a Coriolis force, and this kind of looks like centrifugal force, but is directed inwards instead of outwards. So something weird is happening here, but actually nothing weird is happening. This is actually already the sum of the centrifugal force and the Coriolis force, and if I don't forget about it, I will show you that a bit later. So remind me if I forget about this. Just taking a quick look at the chat. AstroRex is saying, asked me 5 years ago if I'd be tuning into a stream called All Things Coriolis. Yeah, so that's that. And Durango is yeah, took AstroRex up on the offer and just asked about this. Yeah, but yeah, I'm glad that you tuned in. Okay, so yeah, so that's what inertial and non-inertial frames of reference is about. So to sum up, an inertial frame of reference is one where we tally up all the inertial forces. When we tally up all the forces caused by interactions, then not the inertial forces, the real quote-unquote forces, the forces arising from interactions. If we sum them all and they come down to zero, then the object in this reference frame is not moving or moving along a straight line. Or basically this also works for when the forces don't sum to zero. So basically if the forces don't sum to zero but to some value, then in this frame the acceleration of the object will be just this total, the acceleration will be just this total sum of forces, this net real force divided by m. And if it's like this, then the reference frame is inertial. If we tally up all the forces caused by interactions and we discovered that the total acceleration does not equal this, then in order to make it equal, we basically add some inertial forces, and we basically maybe I should write it in the other way around. So I should say that inertial forces are basically by definition like this. Okay, and also multiply this by mass. And that's basically what we call the inertial forces. We take the acceleration of an object, we subtract all the real forces, and the thing that is left we call the inertial force. And this might seem a bit backwards, but this is a pretty good definition actually. Also, sometimes we can say that inertial forces are those forces that we can cancel by changing the frame of reference. So in this case, we see that if we switch to a reference frame that is rotating relative to this one, then this force will cancel out. We will find a reference frame, and this reference frame was relative to this rock, right? So in this reference frame, it will turn out that we don't need any inertial forces because the acceleration of the tree is perfectly explained by the net real force. And so we will call the frame of the rock inertial, and we will call the frame of the roundabout non-inertial. It might not be immediately obvious in reality which frame is inertial and which is non-inertial, because as I said, this from what I said, we can conclude that this depends on how well we can tally up all the forces caused by interactions, and how well we can measure the acceleration. It might turn out, for example, if we are on a rotating Earth, right? So let's say the Earth is rotating here. So actually, there will be a force of gravity here, and there will be a centrifugal force. So the frame of the rock will not actually be inertial, but it's not immediately obvious, because it's really hard to measure all the forces caused by the interactions directly. And so it is really hard to notice that they don't exactly balance, and that we actually need another force, and this would be in this case the centrifugal force caused by the Earth's rotation, to actually have these forces balanced. So that is, yeah. So in reality, it can be non-obvious, and sometimes we need some more sensitive experiments to actually check if the frame of reference we are using is inertial or non-inertial. And for example, Foucault pendulums supply such a sensitive experiment that will allow us to check that the frame of reference that is tied to the ground is in fact non-inertial, because if we tally up all the forces that we have, all the forces caused by interactions, it will turn out that we can't really explain the drift of the Foucault pendulum. And if we take the assumption that the Earth is rotating and we actually calculate the forces in the rotating frame of reference, it will turn out that it matches the drift perfectly. So that is one thing. Well, okay. Let's move on. Okay, so what I want to say is how the forces work so a quick summary of how the forces work in a rotating frame of reference. Wow, I see we have more and more people. So welcome H. Jasper E. Welcome Gary Y. Benga. Welcome Earth is Life, and welcome WS. Nice to see all of you here. And yeah, I see that Gary Y. Benga is saying that everything I'm saying is silly and it's complete nonsense. Well, you're welcome to think that. Okay, let me just take a quick look. Okay, oh, and we have another watcher, but I won't even try to pronounce the name. But hello, nice to see you. Unfortunately, I have no idea how to pronounce Turkish, because I assume that this is Turkish. Okay. So yeah, so next thing, how can we calculate the inertial forces? Where do the inertial forces come from in a rotating reference frame, and how can we calculate it? So let's assume for a moment that we have this roundabout that is rotating, and we have so basically we have some axis. Let's say this is the y-axis and this is the x-axis, and it's rotating around the z-axis, and we have some object, and this object is moving. Okay, so when we look from the outside frame of reference, from the frame of reference that we assume to be inertial for now, so it will, let's say it moves with velocity v. And so at some point in time, it is in a point which we can describe with a vector of position r. And so after some time delta t, let's say this is the vector v times delta t, so this will be the change of position. It will be, okay, no, because now that is exactly the mistake I made before. So no. So let's say we are looking now from the frame of reference of this, from this rotating frame of reference. So this r, let's call it r prime, so that, and this will be x prime and y prime. Those primes will mean rotating frame of reference, and it is moving at a velocity v prime. And so it moves to some place r prime plus dr prime. So the position changed by dr, and this dr is just v prime times some time dt. Okay. So let's now say what is the velocity of this relative to an inertial reference frame. So if this is rotating at an angular velocity of omega, then v, the velocity in the inertial reference frame, will be v prime plus omega cross r prime. Okay. And here, and when it moves to here, it will have some different, it will maybe have some different velocity. Let's call it v prime 2. So the point here is that this v remains constant. So if we take this v and say that it's also here, but at this point v is equal v2 prime plus omega times r prime plus dr prime. So these two are equal, and if we do this, now you will be, you will see one thing in a moment. If we say that these are equal, and if we rearrange these, we will say that we will get that v, I'm making a mess of the screen, but hopefully you can follow, that the change in the v, in velocity, is equal to, so we subtract these two from, so if we rearrange this, we move v prime to this side and we move this part to the other side, and we get that this omega times r prime cancels out, and we get minus omega times dr prime, and we get that this is minus omega times v prime times times dt. But something is wrong here, because if we check, let me just, okay, I actually have this already open. So if we check on wiki, for example, for the Coriolis force, we will see that it should be minus 2 times. So what we got here is minus omega times v. Okay, so this is dv, this is dv prime, and now if we divide both sides by dt, we have that acceleration is dv prime by dt, and this is minus omega times v prime across v prime. But if we look at wiki, we see that it is supposed to be minus 2 times omega times v prime. So what happened here? Actually, I omitted one important thing. So during this time where this object passes from here to here, this frame of reference rotates a bit. So the v here in this point will not actually be the same v as here, it will be rotated. So we can't really say that this is like this. This is a rotated v, I will denote it like this. And this is rotated by an angle of omega times dt. So how can we rotate v by angle omega times dt? So actually it's rotated in the opposite way because the roundabout rotated by omega times dt, and so in this reference frame the velocity vector rotates to the opposite side. So basically, if we had this velocity v like this, and the reference frame rotated this way, then we have to rotate this vector this way. So it will have some dv here. And what is this dv? This dv will actually be just omega times v minus, actually, because omega times v would be in the other side, omega minus omega times v times dt. So we need to add this part to v on the other side. So if we do this, we will say that here this is actually equal to v minus omega times v times dt. Oh, again, I used the cross instead of just regular multiplication. Okay. Okay, and v was equal to this, so we can actually substitute it here. And now I'll get confused, so let me just copy this on a new page. Sorry. Okay. So we have like this. We have v prime plus omega times r prime. So this will be this v part here minus omega times v. And v, I again will substitute this part, so this is v prime plus omega times r prime dt, and this is equal v2 prime plus omega times r prime plus omega times dr prime, but this is just v prime times dt. Okay. So now if we rearrange this, we will say that dv prime, which is equal to just the difference of v2 minus v2 prime minus v prime. Sorry, again. And this is equal to, we move v prime here and we move everything to the other side. So this part actually is the same on both sides, so it cancels out. And we have that it is minus omega times v prime times dt minus omega. So it's this part here. Now this part here will be again minus omega times v prime times dt. So we have again this. And we have one more term, which is omega cross r. So it is equal minus and dt, of course. So if we divide by dt, we have dv prime by dt equals minus 2 omega v prime minus omega cross r. And finally we got the 2. This is Coriolis, and this is the centrifugal force. Right, so this mathematical part probably might have scared some of you away, but yeah, basically if you know some vector algebra and cross products and stuff, this should be, maybe you'll have to sit on this for a while, but this is one of the ways you can derive what the Coriolis force is and what the centrifugal force is. But the important part I want you to take away from this is that this popular explanation, which I did before, that, well, basically this conserves momentum, so the v here is the same as the v here, and if we calculate, then we will actually get this, which is wrong. We will get a wrong result if we just rely on the conservation of momentum. We also need to take into account that the frame of reference rotates. There is also another way of looking at it, which is
You can look at it from the point of view of conservation of angular momentum, but I think you can't really derive the whole equation if you just start from there. So the best way is probably to think that, okay, this v was conserved. So in the inertial frame, the object had the same speed here as it did here, but it is now in a place where the rotation, the speed of rotation is in a different direction, and possibly with a different magnitude. So this changes, and this gives rise to this minus omega times v prime. But also, this frame rotated in the meantime, and this gives rise to another term like that, which then gives the 2 in front of it, and to the centrifugal force. So that's important. And so, when we have this, let's look again at the tree in the reference frame of the roundabout. So if we look at the motion of the tree, so we have I'll draw it in white again. So we have this person on the roundabout, and we have this tree here, which is at some r, and it is going with some velocity v. But we know, because this tree was at rest in the inertial reference frame, we know that this v is equal to minus omega times v, times r, sorry. So now, if we calculate the total inertial force that is acting on this tree, we will have that F inertial is equal to minus 2 omega times v, but this is cross product v, but v is minus omega cross r. And we also need to subtract the centrifugal force, which is omega cross r. So this, actually, the minus here cancels out, and we have 2 pluses, and we see that this is the same as this, except we have 2 times this, but minus 1, so we get that the total is omega cross r. And if we calculate what this is, it actually turns out to be a vector that is towards the center and with magnitude omega squared times r. So that is basically why we get this inertial force that is towards the center. It's actually the sum of the Coriolis force, except Coriolis is here, is in this direction, and is 2 omega squared r, and there is a centrifugal force that is in this direction, and it's omega squared r. And the sum of them is omega squared times r towards the center, and that is how, from the perspective of this reference frame, of the reference frame of this spinning roundabout, this tree seems to go in circles. And okay, let me consult my notes if that is everything I wanted to cover from this point of view. I think yes. Okay, so in my videos recently, let me just quickly load what I mean. So in my videos, I showed some simulators I've created. So I've shown the 2D simulators of motion if in a rotating reference frame, but now I also have a 3D simulator that basically is supposed to simulate a rotating Earth, and this is what I want to show you now. After an hour and 20 minutes, apparently. Wow, this took a long time, longer time than I thought. So I will show you the simulator right now and what it can do. Let me just launch it. Okay, where do I have a free... Wait, okay. Let me free up this space and let's go. Okay, so this is what it looks like. So now I can show you some things that I actually discussed a moment ago. So for example, let's add an object. So let's not add an object. Let's not add objects first. If I just start the simulation, you can see that we're rotating with the Earth. So we are now an observer in the non-inertial reference frame. So whatever we're looking at right now is shown from the perspective of a non-inertial rotating reference frame, but we can change it. We can change the speed of rotation of the reference frame, and right now the reference frame is not rotating. This is the inertial reference frame, and now from the perspective of this reference frame we can see that the Earth is rotating, but the sky is not. So basically what I'm going to show you is how stuff moves from the perspective of these two inertial reference frames. Important thing. In this simulator, I'm not really designing the trajectories of the stuff we will see. So when I put some objects in the scene, when I put some objects in the simulation and they start to move, the way the simulator calculates it, I can actually show you the source code, because why not? Some of you know coding, so I can just show you the source code. Okay, so this is in Rust, and if we look at an object, basically an object is something that has a position and velocity and some properties not related to physics, like color, radius. Okay, this is related to physics because basically I also added the possibility to change how an object is influenced by gravity. So this here is just the gravitational parameter of the Earth for that object, so I can have some objects that are affected by gravity and some that are not. It's a bit it might not be the most straightforward way to do this, but this is how I did it. There is also a drag coefficient which is not used right now. There is a friction coefficient that can be used. It can be defined for the object. I will show you what happens. It's not the name friction might be a bit misleading, because this is actually some more like drag, but also not quite, because this actually creates a force that is proportional to velocity. So when an object is moving at and also only when it is on the surface of the Earth, that's why I called it friction. But basically when it's moving along the surface of the Earth, it will experience a force contrary to its velocity relative to the surface of the Earth, which will slow it down, and at some point it will stop. The attractor part is just so that I can create Foucault pendulums, so I can define some additional force that depends on position that acts on the object. So in the case of Foucault pendulums, they are just attracted to a single center point and they are oscillating around this center point. So that's an additional force. And there is this object state. Okay, so this is just whether it's in flight or on the surface, because the forces are calculated slightly differently when the object is on the surface than when it is in flight. I will just show you in a moment. So the main point here is basically this function that is called derivative. And it's called derivative because basically it calculates the time derivative of the state of the object, and the state of the object is position and velocity. So time derivative of that is velocity and acceleration. So velocity is straightforward because we already have it in the object, and acceleration has to be calculated based on the position and velocity. And so as you can see, we have derivative in flight and we have derivative on surface. So derivative, let's start with derivative in flight. It's straightforward. So first, since I'm working with different reference frames, the positions and velocities themselves remember which reference frame they are defined in, and I just stored this as the omega parameter, which is just the angular velocity of the frame of reference. So if the velocity is defined in the non-inertial frame of reference, then this omega will be non-zero. If it is in the inertial frame of reference, this will be 0. And same applies to position. And position also stores the time, because this actually is important in conversions between different frames of reference. So So the first thing this calculation does here is it just converts the velocity to the reference frame with angular velocity that we want, that the position is defined in, so that all the calculations are done in a single reference frame. Potentially, it's possible for the velocity and position in an object to be stored in different reference frames. So in case that happens, this conversion is being done so that both of them are in the same reference frame. And then the calculation of acceleration basically takes gravity, and the gravity only depends on position, and this basically gravitational parameter, plus centrifugal, plus Coriolis. So that's all. But if omega is 0, you can see that, for example, when we have a position, centrifugal force is being defined by the position vector times omega. So if omega is 0, centrifugal force will be 0. In the case of Coriolis, we have basically this, what I showed you, it's minus 2 times velocity cross product vector of angular velocity cross velocity. And again, if velocity is 0, this will be 0, and if omega is 0, this will also be 0 because this vector will be 0. So basically, if we're working in an inertial reference frame, then this will be just gravity here. And that's it. And so then it just calculates the velocity as, well, we just copy the velocity from the object and calculate the acceleration as acceleration under gravity. And if omega is non-zero, there will be also non-zero centrifugal and Coriolis terms, and that's it. On surface, it's a bit more complicated. So here you will notice that I'm not calculating the gravity and centrifugal force, and this is explained here. Basically, it's because what I need to calculate when the object is on the surface is just the tangential force. So basically, in the force perpendicular to the surface, it will be cancelled. Well, not necessarily cancelled, but but I will go to that in a moment. So the force that is in the direction perpendicular to the surface will be cancelled by the reaction force from the ground. And so the really important forces are in the direction tangential to the surface. And so basically the reaction force will cancel the sum of gravity and the centrifugal force. Basically, the surface of the Earth is everywhere such that the direction perpendicular to it is parallel to the sum of gravity and centrifugal force. So I don't need to care about the centrifugal force and gravity here because it will be cancelled by the reaction force. Maybe not exactly, because if the object is moving, then its trajectory needs to be curved towards the center a bit, and so in such a case, the reaction force won't cancel the gravity and centrifugal force exactly, but still this will be only in the vertical direction. So I'm calculating the only forces that have horizontal influence here, and that is again Coriolis, that is friction, which I already described, and it's this attraction force which results from this. I'm using for Foucault pendulums from this attraction from a single point. I'm actually also using this attraction force for cyclones. I will show you cyclones in a moment, because I'm trying to simulate a force that is pulling the particles towards the center of the cyclone, but it actually doesn't work that well. Well, I would need to adjust the attraction force for cyclones a bit more, but okay. Then basically this calculation here calculates the surface normal, and then this calculation here makes sure that the acceleration that is normal to the surface, perpendicular to the surface, is sufficient so that the path is along the surface, is curved at the same rate as the surface. Actually, not quite, because I'm calculating the radius of curvature here, which is based on the meridional radius of curvature, and it's not the same in all directions, so this is actually a mistake in the code, but it doesn't matter anyway in the long run because it's close enough to the correct value. So this basically only calculates the proper vertical component. So I see that Eric Okay, just I'll go back in the chat for a moment. Okay, I see Real Cygnus was asking if Rust has decent graphics lib. You know, I'm just using OpenGL. It has a nice library for using OpenGL, and this is what I'm using here for this program. Yeah, so Real Cygnus is asking if I'm rendering to a vid. No, this time I'm rendering in real time in OpenGL. And I'm also using a nice interface library that can be combined with this OpenGL rendering library, and I can render the interface directly to the scene. It's quite convenient. And I see Eric is pointing out that centrifugal force will not be vertical at most latitudes, and that is true, but that's not quite what I was going for. Okay, so let me just try to draw this. So let's say this is the axis of rotation. So the axis of rotation is vertical, and we have the surface at some latitude here. So in this case, the centrifugal force will act away from the axis of rotation. The reaction of the ground will be perpendicular. So let's say we are talking about an object that is at rest for now. So this is an object that is at rest relative to the surface. So we have the reaction force, we have the centrifugal force, and these two will be exactly balanced by gravity, which will be directed somewhere here in this case. So it will be exactly equal to, I'm not great at drawing, it will be exactly equal to this, only in the opposite direction. Okay. So now if the object is moving, its path needs to get curved towards in the vertical direction. So it needs some net force acting here in this direction, so that its path along the surface is curved at exactly the same rate as the surface. But as you can see, I can achieve that by only modifying the reaction force. So if I just say that this is like the default reaction force that is balancing centrifugal and gravity, then if I change this, then I can just say that this is some reaction force plus some change, some difference, and then I also will have Coriolis, which will be, I don't know, which will be directed somewhere. And so if I sum all the forces, then I will have that it's force of gravity plus force centrifugal, let's write it like this, plus force Coriolis plus reaction plus dr, right? So that is the total force acting on this, and it is supposed to be vertical. But note that this, and this is in total 0. So basically I only need and plus some other forces implied by the simulation, like this attraction or something, or friction. So these forces come down to 0, so the total force will be just F Coriolis plus this dr and plus all the other forces needed by the simulation. So that's why, to calculate the final force acting on the body, I don't need to care about the gravity, about centrifugal, because they will cancel out with this default reaction force, let's say. Well, the actual reaction force is this, but I can only care about the difference of the reaction force from this one that would exactly balance gravity and centrifugal. So this is this is vertical. So I can just calculate Coriolis, I can calculate the other forces, and I can add a vertical component that makes the net vertical component to be equal to what I need in order for the object to follow the curvature. Eric is asking if I'm using the WGS84 ellipsoid for the Earth. Yes. Yes, for the shape of the Earth I am, so I can show you. Wait, where was I showing them? Here, okay. So if we look, actually it's a bit incomplete, but you can see that I have an equatorial radius and polar radius, and I believe I took the values from WGS84. You can double check me. Then I also calculate the eccentricity squared. So here are some functions that are basically attempting to calculate which direction is the surface normal at a given latitude, and convert latitude and longitude and elevation to the position XYZ in the reference frame. This turns out to be a bit complex because of the difference between geocentric latitude and geodetic latitude. So I've looked how it should be calculated and basically implemented these equations. But what is not correct still in this model is that if you look at how I'm calculating gravity, then gravity is calculated as just being minus gm divided by r squared in the direction of basically towards the center of the Earth. And it's not quite correct. The actual force of gravity is not exactly towards the center of the Earth, but it's a good enough approximation. And where it matters, I'm really assuming that, well, gravity plus centrifugal force is exactly vertical, so that is what is really important, and what will be important in a moment when I show you what happens to objects, because they will do some really non-intuitive things. And that's kind of one thing that I also wanted to point out, that because flat earthers will just accuse me of making this program showing what I wanted it to show. So no, I'm showing you this code to point out that what I made here was really just implement these laws of physics. It's just calculating the forces acting and then calculates how the object will move under the influence of these forces. So that's what I wanted you to take away from me showing you the code. And one really important thing here, and what was awesome to me, is I definitely did not code the things to behave the way I wanted them to, because this simulator actually showed me something I didn't expect. It showed me something that surprised me. I was totally taken by surprise by this, and for a moment I thought that it was working wrong, that it was buggy, that I made a mistake somewhere, and I had to think for a longer while to figure out that no, that actually what the simulator showed me was correct, and it was me who was mistaken about what should happen. So I actually learned something from it, and that is also why simulations are really, really important in physics, because physicists can actually learn something from the simulations. The very reason physicists do simulations is to learn something from them. So it's not always obvious what a physical theory will imply, what consequences it implies. You can try calculating it on paper, but sometimes it's just easier to make a computer simulate for you the world according to the laws of physics that you are postulating, and then see what should happen if these laws were true. So this is basically what I did here, and it surprised me. But yeah, I learned something from it. So yeah, let's go back to the program. So I will show you what it can do. So let's just start with a single object, which I call a free object, which basically means that it has no it has no attractor, let's say. So nothing attracts it, and it's just a single object that is moving under the influence of gravity and centrifugal and Coriolis, and if I define it here, friction and no, drag, no, because I'm not simulating drag right now. So let's put it at a latitude of 45 degrees, let's say, and let's put it at a zero velocity. This velocity is relative to the surface. So we have just an object here on the surface. And if we start the simulation, then as expected, nothing happens. We can see it's okay. Its velocity actually increased to 0.2, which I'm not quite sure why it happened. Probably some kind of inaccuracy from the calculations, but as you can see, it doesn't increase more. So So basically it doesn't move. If it didn't move, it doesn't move, it will just rest on the surface. But we can draw the forces at play here. And let me turn off the surface. So the forces at play here are gravity, and gravity is this long yellow thing. Okay, so let me maybe scale this down a bit. Okay, so this is gravity. And the green arrow that already disappeared was the centrifugal force. And you can see what is the scale here. How much smaller is the centrifugal force than gravity. So it's that small. But those are the two forces that are acting. This doesn't draw the reaction force. If it did, it would draw another force here perpendicular to the surface. But it only draws the forces that are actually simulated, like calculated directly. Okay, and if we edit state and if we add some velocity, okay, so maybe let me show you one more thing. If I change the reference frame, okay. So what happened here? Okay, that is nice. So when I change the reference frame to the non-rotating frame, what happens is the centrifugal force disappears because there is no centrifugal force in a non-rotating frame. And what appears is this red line, which will be visible clearer maybe like this. And this red line is the path this object took in the inertial frame. So if it didn't move in the non-inertial frame, it means it was rotating along with the surface of the Earth. And so as the time was passing, let me reset. And so if we look from the inertial reference frame, in the inertial we can see that the velocity changes. It has 0 velocity in the non-inertial frame, and it has 3 to 9.4 meters per second in the inertial frame. And if we start the simulation, then it moves in the inertial frame together with the surface of the Earth, and it moves in a circle around the axis of rotation. And so, as I said before, since it moves in a circle, there needs to be a force towards the center, and there is actually. This force towards the center is provided by gravity, which has a component that is parallel to the surface. So yeah, if basically if the combination of centrifugal force and gravity is perpendicular to the surface, it means that the gravity itself is not. And so if it's not perpendicular to the surface, it means that it has a component that is tangent to the surface and that is perpendicular to it. So this basically this component that is tangent to the surface is what provides the force the force that is needed to curve this path of this object into a circle. Okay, and so now let's see what happens if I add some velocity. Let's 200 meters per second. So in the again we are in the non-inertial frame. Let's draw not the velocity. Let's draw the forces now. So now if we draw the forces, we can see that another blue arrow appeared. Let me increase the scale a bit. So we have the centrifugal force, which is green, and the blue arrow is now the Coriolis force. So because this has a velocity now in this reference frame, then the cross product of the angular velocity and velocity is non-zero, and so there is some non-zero Coriolis force. And so all the forces that are acting are now these two and gravity and the reaction force. And the motion now, if we start a simulation, you can see that in the non-inertial frame it starts going east, but then it gets deflected to the right, so to the south. That's because if we look at the Coriolis force, it actually it acts in the direction that is perpendicular to both the axis of rotation and the velocity, but this is not perpendicular. Wait, maybe I'll be able to show it to you better because I actually implemented rotating the camera. Okay, so maybe you can kind of see here that this Coriolis force is not at all perpendicular to the surface. So that is why it has a horizontal component. It has a component that is tangent to the surface, and it will curve the path of the object. Let me try to return to this view. Okay. And so it does. Basically, the object starts turning to the south, and if we continue, it will continue turning. And you will notice that the Coriolis force actually decreases once the object moves south, because it is closer and closer to the equator, and so the velocity is getting more and more parallel to the axis of rotation, and so the Coriolis force decreases. But if we wait long enough, it will probably cross the equator. Yeah, the Coriolis force already disappeared almost. And so the object crosses the equator. And now on the other side of the equator, it starts turning the other way, because the Coriolis force is now to the opposite side. Okay. So that is the path in the non-inertial frame. But if we looked at it from the inertial frame, we can see that it looks more like this. So let's rewind time to the beginning. So we can see that it had actually a larger velocity here, and that is to be expected, because in the inertial frame the velocity of the object is the velocity of the object relative to the surface plus the velocity of the surface. So it's larger than in the non-inertial frame. And as time passes, it also starts moving to the east together with the surface of the Earth, but it starts getting deflected to the south. But actually, if you look at it, you might expect that it should move along an orthodrome, so it should move along a great circle. But if you look at this, let me try. You can see that this isn't quite a great circle, it's curved. And that is what surprised me, but that is also what is actually correct. So yeah, you can see that this is the path it followed in the inertial frame. So if we just looked from one place, we would see it moving and the Earth rotating, and basically this is the path it would take. Okay. So yeah, so it might be a bit surprising that this is not an orthodrome, and if you've seen, let me find the website. You might have seen Walter Bislin's website, How Airplanes Correct for the Coriolis Effect. And here, when he simulates planes going around the Earth, what he's doing is basically he's assuming that a plane going, that the plane's path in the inertial frame will be an orthodrome, so that it will go around along the great circle. And so if you try to follow this, you will see that the path along a great circle in the inertial frame is something like this in the non-inertial frame. And everything is cool, but the problem is, so let's put the speed down to 0. So if we have a plane that is moving at 0 speed relative to the surface, we would expect it to stay on a single point on the surface. So we would expect it to go along the line of parallel, right? Along the line of constant latitude. But if we do the simulation here, it goes along a great circle, which means it starts rolling down in quotes, towards the equator. And it will cross the equator, and then on the other side of the equator, it will start rolling back north. So what is happening here? So what Walter Bislin is simulating here would be correct if the lift of the plane was was countering gravity and gravity only. So if the lift of the plane was parallel to gravity, what we would see in the inertial frame would be that the total force would be directed towards the center. Well, would be directed where gravity is directed. So then the path would be approximately a great circle, because the force would be approximately towards the center, and yeah, we would get a geodesic, an orthodrome. But if a plane is flying level, then the lift is directed vertically, and vertically is not parallel to the force of gravity. So Crowexy is writing, here comes the confusing part. Yeah, we discussed this already. So if a plane is kept its wings level and it was flying level, basically the lift would be directed vertically. So it would be counteracting not just the force of gravity, but the sum of gravity and centrifugal force. And so basically this there would be a component of the sum of lift and gravity that would be directed towards the pole, and it would curve the path a bit towards the pole. So it's probably a bit confusing, so maybe let me try it. Let's try again this example here. Here we don't really, let's say we don't have lift, it's resting on the ground, so we have something that is not moving relative to the ground. But here Walter assumed that the force of reaction of the ground would be parallel to only gravity, which means that in the non-inertial frame of reference we have nothing that will balance the centrifugal force, and centrifugal force acts away from the pole, and so we see an effect as if it started rolling towards the equator, because that's where the centrifugal force is telling it to roll, and the curve towards the right is due to Coriolis. So if it was like Walter Bislin is simulating, then basically things would roll towards the equator, yeah, because of the centrifugal force. But since if we have something resting on the ground, the reaction force is actually vertical, so it's countering the centrifugal force as well, then we shouldn't see this rolling. We should see it resting at a single point on the surface of the Earth, and the path in the inertial frame of reference would not be the great circle, but it would be the circle of latitude, the parallel, right? So yeah, so that's how we can see that, well, if this was the assumption that Walter Bislin made, that okay, plane that is not correcting for anything, okay, so wait, no, it should be ballistic, no friction, it doesn't matter at this point. So yeah, so if the assumption here was that the force of lift is countering gravity and gravity only, then I would say this is correct, because if we only counter gravity, then this is what we would expect. Only in practice it's hard, because in practice countering only gravity would require calculating where the centrifugal force is and then adjusting for the centrifugal force so as not to counter it, because if you just orient your plane horizontally, you automatically counter the centrifugal force as well, which is why I think this would be a very artificial assumption. And actually Walter seems to agree with me, because if you look here, he's saying that the effective gravity vector is the vector sum of gravity vector pointing to the center and the centrifugal acceleration vector, because the lift force acts exactly opposite to the effective gravity vector. The centrifugal acceleration is automatically cancelled if the airplane flies level with respect to the ellipsoidal surface. In the calculations above, the correction for the centrifugal acceleration is contained in the lift force and not explicitly displayed, and this is what, in my opinion, is an error on the website. Because if this assumption was actually made, then the path wouldn't be a great circle, because the plane would be countering the centrifugal force, which is not present in the inertial reference frame, which would curve the path of the plane towards the pole. But since the plane in this simulation moves along a straight line, along an orthodrome, it means that it's not countering the centrifugal force, and this is what is causing the plane to kind of roll downhill towards the equator, because the centrifugal force kind of acts like the force downhill in this case. So I think that Walter Bislin made a mistake on this website, and if he doesn't watch this stream, I will actually contact him and tell him what I think about it, because I think, I actually, don't take me the wrong way, because I think Walter Bislin is great, and I think his website is awesome, and he has a lot of hugely useful stuff, and it's basically great, and I recommend it to everyone. So don't take me as if I'm bashing on Walter Bislin, because I really think he's awesome. I just think that he made a small mistake in this particular case, and I'm going to contact him about it, because I think it's just worth bringing it to his attention, because I don't think it's a big problem, because as I said, if we just assume that only gravity is countered, then this is correct. But it looks like the intention was to have a plane to simulate a plane that is flying level and is countering both gravity and the centrifugal force, and in such a case this is incorrect. And that's exactly the thing that my simulator taught me, because I also didn't expect this. So let this be some sort of a measure how counterintuitive this is, because I made the simulator and I still didn't expect this to happen. But if you think about it for a while, then actually you will expect, you should expect the centrifugal force, the force. If it's countering the centrifugal force, then you should expect there to be a force directed towards the pole, and you need to put the ball on a non-rotating Earth to explain this properly for some people. So what? Probably I don't really have in my simulator right now a possibility to turn off the rotation completely. It shouldn't be that hard actually, because I just coded it as a constant, and it would be possible to just not make it a constant and make it a configuration value. But one thing that CrowXC did, and he's present right now, this is actually an awesome demonstration of what I was just talking about. So he did a bit of a non-intuitive thing. So he placed an object at a high latitude. So he placed it at 89 degrees north, and he made it go south. So let's make this object go, 200 meters per second to the south. So we have an object here, almost at the North Pole, and so the velocity is directed south, and you can see that if we switch to the non-rotating frame, it only deflects slightly to the side, because basically at this latitude, the velocity of the points of the surface in the inertial frame are very, very small. So it doesn't make much of a difference if we look from the rotating or from the non-rotating reference frame in this case. But if we look from the inertial, if we look from the point of view of the inertial reference frame and we start simulating this object, let me accelerate time a bit. It goes towards the south and then turns back towards the pole, and then goes across the pole to the other side, but then it decelerates and starts going back towards the pole again. And so this is what surprised CrowXC, and what surprised me at first again, because I already knew about this component of the force that acts towards the pole. But this surprised me again. But this is actually what is expected, because let's look what it looks from the rotating reference frame, and from the rotating reference frame it basically looks as if the object started south but then got curved by the Coriolis force and made a circle, and went almost exactly back to where it started, and then made another circle, etc. But what is really counterintuitive is why, if we look at from an inertial reference frame, why the hell does this object turn back? Because you would expect it to just roll in this direction and then go to the southern hemisphere and then roll over the southern pole and go back from the other side, but it gets slowed down and starts turning backwards, and that's exactly because of the oblateness of the Earth. So if we look at the object, for example, in this place, let's maybe, okay, so somewhere here, if we look at the object here, so its velocity is 0 in the inertial reference frame, but it's non-zero in the non-inertial reference frame. Yep. Okay, so yeah, so if we look from the inertial reference frame here, we have two forces. We have gravity, which acts roughly towards the center, and we have a reaction force, which I'm not drawing here. If I draw forces and I don't draw the solid surface, then we have the force of gravity. I'm unfortunately not drawing the reaction force, but you wouldn't see the difference anyway. But the point is, the reaction force is vertical and gravity is not. And so the net force here has a component that is parallel to the surface and is directed towards the pole. And so this is precisely what turns the object back from rolling towards the south. This component of the reaction force that, well, the reaction force has no component that is tangential to the surface, but gravity has. So this component of gravity that is tangential to the surface actually slows the object down and then makes it go back towards the pole. And if you think about it, that is exactly the same. This is precisely the same thing that makes the object go in circles when it's at rest relative to the surface. So if we have an object okay, maybe I won't do this. But when we had an object that was at rest relative to the surface and the Earth was rotating, it was making a circle, right, in the inertial frame. So there was a force directed towards the pole in the inertial frame already, only it wasn't as counterintuitive because you could just think about it, okay, so it's just laying down on a single point on the surface and it's rotating with the whole Earth, so of course it is making a circle. But if you look at the physics of it, if it's making a circle, then is a force directed towards the center of the circle. And this force directed towards the center is precisely this component of gravity. And so here we still have this component of gravity directed towards the pole, only this time we don't have a circle, we have an object that is just moving north-south. So it gets a bit less intuitive because suddenly it goes back and starts rolling back towards the pole and it's just oscillating around the pole. So it's weird, but if you think about it, it actually does make sense. So Krauexy is writing, so if a ball is set near the equator and was denied rotation with Earth or atmosphere, it will roll down to the pole, since the pole level is closer to center of gravity. Yeah, I think we should expect that. Let me, yeah. Weird but true, yeah. So maybe not at the near the equator, so that's correct. So let me maybe try this. So let's say we have latitude of 1 degree, and we will have a velocity east of, and I need to calculate this. Do I still have this open somewhere? Yeah, perfect. So 465 meters per second at the equator times cosine of 1 degree. So I need to convert radians. Okay, it's still almost 465. Let me just see. Let me just do it this way. I'll enter 465 minus, because it needs to be to the west. And let's look in the inertial, okay, and in the inertial reference frame it's 0. So we have something that is not rotating with the Earth, but in the rotating reference frame it does have a velocity to the west. But yeah, it's basically exactly countering the Earth's rotation, so it's moving along the surface at exactly the speed the surface is moving relative to the inertial reference frame, and so it's not moving in the inertial reference frame. And if we look at the forces involved, we have centrifugal away from the equator and Coriolis towards the center roughly. So actually the fact that Coriolis has a large vertical component here, it's part of the Oedfeuch effect. So in this case Coriolis acts to increase the weight of the object, and that's basically what happens with the Oedfeuch effect. When an object is moving west, it has an increased weight because of this Coriolis force, if we look from the non-inertial reference frame. But okay, let's look from the inertial reference frame, and we can draw velocities but not forces. Let's draw the surface and let's see what will happen if we look from the inertial reference frame. So the Earth is rotating. This, we explicitly countered the rotation and it starts moving towards the pole. And this is precisely because of this centripetal component of gravity. And then it passes the pole and it goes to the other side, and it should break right before the equator and start going back. And we have it approach the equator. I wonder if numerical inaccuracies don't make it. No, they didn't. Okay. And it started moving the opposite way. And so if we look from the point of view of the rotating frame, what happened in this frame was... Oh boy. Let's go back to the beginning. So in this frame, when we are looking from the point of view of someone rotating with the Earth, it started moving west, and then it got slightly deflected by the remnants of Coriolis to the right, because it's still in the northern hemisphere. It's just slightly north of the equator, so there is a very slight Coriolis force towards to the right as well. There is very slight component of Coriolis to the north. So as it is moving, it starts accelerating north, and then it starts accelerating more and more. Wait, no, this. And at some point it accelerates towards the pole, and then it passes the pole, and then Coriolis basically makes it curve again, and then makes it break right before the equator. So that's how it works if we look from the rotating frame of reference. And if we look at some point closer to the equator, if we turn on forces, we see that there is the Coriolis force here. Oh, and yeah, CrowXC is pointing out that always 465 meters per second. Yep. It's basically always... it's always almost exactly 465 meters per second, because there are no forces acting in the direction of motion here. So basically centrifugal force plus gravity plus reaction cancel out. Well, there is maybe some vertical component left, but it's vertical, so it doesn't act in any horizontal direction. And Coriolis is always perpendicular to velocity, so there is no force here that would increase or decrease the speed of the ball relative to the surface. So if it started at 465 meters per second, it will always go at 465 meters per second. Actually, it says 464.3, and that is actually a bit weird, because I think I explicitly entered minus 465. Yep. So I'm not sure what is happening here. This is a bit weird. Okay, and now it's 465. That is actually weird, because it's not the way it was supposed to happen. Some numerical inaccuracies probably, but I'm also not sure what numerical inaccuracies here, because okay, and it drops to 464.3. Oh, I know what's happening. Because the moment it starts is in the state in flight. So when it's in flight, it drops, it is being simulated in a different way. So the simulation actually simulates a part of its trajectory when it's falling through the Earth towards the center, but then after simulating it basically realizes that, hey, it's below the surface, so I need to put it back on the surface. And when it's putting it back on the surface, it's putting it with the velocity that it already got. So since it fell a bit, it got a bit of a velocity towards the center, and it lost a bit of tangential velocity. And so this loss of tangential velocity is preserved when it's being like teleported back to the surface, and that's why the velocity drops from 465 to 464.3 immediately. So that's actually, you could say it's a bug in the simulation, but that's what happened here. Yeah, and basically, yeah, since the only unbalanced forces horizontally are perpendicular to velocity, and then velocity doesn't change throughout the motion. And that's also how we can calculate very easily what speed it is required to start south from the North Pole in order to cross the equator. Because this velocity is constant, there is no way for any object to cross the equator at any velocity, if it started south from the pole, at any velocity lower than 465 meters per second. So we need 465 and change in order to cross the equator, and if we do that actually, so let's just try. I make it 89.9. I'm not making it 90 because exactly at the pole it's not clearly defined what the directions east and north are, so the simulator might get confused. So I'll make it minus 466 and to the south and not to the west. Minus 466. Okay. So it will start from the pole and go towards the equator, and this time it should be able to cross the equator. I see Eric is asking if the source code for this will be made available. I think I actually already posted a link. Okay, the link to a release is already pinned in a pinned comment under my last video, but it's to the GitHub repository, and the whole source code is available there as well. So you can, for example, find it there, but I will also link it under this stream. So if we try this, then this should slow down to almost zero near the equator, but it should still cross the equator. And it's slowing down, and now it passed the equator and is going towards the south. And if we switch to the rotating reference frame, you can see that the path got curved by Coriolis, but not strongly enough to get deflected back north before the equator, so it crossed the equator and it spiraled to the south pole, and then now it's going back north. And from the inertial reference frame, it just made a circle across the pole and it's going back north. So that's the sort of thing you can do in this simulator. So there are also a few more things I wanted to show. Okay. So I think that's enough about the really non-intuitive part, but I hope I was, well, I tried to be as clear as possible about why this happens, why things that start going south from the North Pole actually get turned back north, even though we're looking from the inertial reference frame. So the way I noticed it actually was when I simulated an anticyclone for the first time. So let's do just that. Let's add an anticyclone at some latitude like 45 degrees. Okay, might be like this. Okay, so what we have here is actually 8 particles, each with a starting velocity in a different direction. And when I start simulating this, they will spread out and they will start curving. And so we can see that as they go further and further away from the center, they get curved to the right more and more. And so if we look at this system as a rotating circle, we can see that it starts rotating clockwise, right? So an anticyclone is rotating clockwise in the northern hemisphere. And that's something that actually Sleeping Warrior commented somewhere under Rage's video, that if it was Coriolis effect that caused the rotation of hurricanes, then anticyclones wouldn't be possible. No, they would be possible. They are precisely simulated here in this simulation that basically simulates the effect of Coriolis. Yeah. And the way I noticed this non-intuitive thing was, now if we start with this and we switch to the inertial reference frame, we can see that the paths of these particles, none of these paths is along an orthodrome. They are all curved towards the North Pole, more or less. And that's precisely because of this effect that I was talking about regarding the planes, regarding these particles that were turning back, etc., etc. It's because gravity is not perpendicular to the surface, in short. So there is a component of gravity that is along the surface towards the pole, and that causes all these objects to turn towards the pole. And so if we simulate them, they are going and they are basically rotating in this funny way. And you can see that the particles that went north are now getting curved more than the particles that went south, because the Coriolis effect is stronger the closer you are to the pole, because near the equator basically it's only east-west and vertically, and that doesn't really make a difference. Right, and so if we add another anticyclone at the southern latitude, I already showed this in the demo, but let's just show it for completeness. So if we have two anticyclones and we simulate them, then we can see that the rotation in the southern hemisphere is the opposite way than in the northern hemisphere. These turn clockwise and these turn counterclockwise. But these are anticyclones, and if we do cyclones, so let's remove those, let's add two cyclones. One at 45 and one at minus 45 again. So cyclones are basically particles that are some radius apart from a central point, and all start with velocities towards the center. And also they experience some slight force of attraction from the center, but it doesn't really change much in these scenarios. So if we start simulating that, we can already see that they got deflected and they start rotating counterclockwise in this hemisphere and clockwise in this hemisphere. And this is exactly what we expect from particles affected by Coriolis. Yeah, and now they just circled the center and went back away. In a proper cyclone, basically the friction, the viscosity of the air would cause the particles of the air to not bounce back and away from the center again, but they would just start orbiting, like circulating counterclockwise around the center here and clockwise around the center in the southern hemisphere. But here I'm not simulating such complex phenomena, and I just have particles that are slightly attracted towards the center, and it basically causes something like this. But yeah, if we look back and if we see in the inertial reference frame, it looks a bit weird. Let me turn off the velocities so that they don't clutter the image, and they basically converge and rotate and diverge again. And in the opposite way here. Right. And yeah, also one thing that I already showed in the demo, but not here, is Foucault pendulums. And I won't be creating a lot of them. Let's use some higher latitude. So basically, if we start with something that is oscillating north and south, you can see that it will get deflected due to the Coriolis force. And what I find quite interesting here is what it looks like, but I'll let it complete like a quarter of a turn at least. And actually, okay, so it performed a quarter of a turn in 25,000 seconds. So the whole circle would take it about 100,000 seconds. And coincidentally, 100,000 seconds is pretty much so what we expect. If I remember correctly, we expect the time of the full circle to be 24 hours divided by the sine of latitude. Right? Yeah, that would be correct. So this is 60 degrees, sine of latitude is about 0.866, and 24 hours is 86,400 seconds. So this divided by 0.866 is about 100,000, so that seems correct. And if we look from the inertial reference frame, we can see that it actually is trying to oscillate in the same direction all the time, but the fact that, well, the surface is getting oriented in a different direction in different places, it's causing it to turn slightly, and that is pretty much why it only oscillates. You can think of it as the reason why the Foucault pendulum makes one circle in 24 hours only at the pole, and in more time farther from the pole, because it can't really oscillate still in the same plane, because the same plane is no longer perpendicular to the surface of the Earth, so it needs to deviate slightly, and you can see what happens with it here. And so basically it continues oscillating, and it continues oscillating in almost the same direction, but not quite the same. And again, I once again stress that I didn't code this drift of the Foucault pendulum by hand, so there is nothing in the code that says, okay, take the Foucault pendulum and rotate its plane of oscillations in this and this speed. No. The only thing this is simulating is just a moving object and forces acting on it, that's it. And the forces are according to physics, basically. And if we switch to the rotating reference frame, again we can see that it just drifts around the point. And if we actually add the Foucault pendulum directly on the pole, well, I'll do it again at 89.9 so that it's well defined what direction it should have. So if we start like this, and if we switch to the inertial reference frame, you can see that the one that is over the pole oscillates constantly in the same direction. But from the point of view of the non-inertial frame, it looks like drift. I see Real Cygnus is writing that this is one of the most interesting projects I've ever seen. So thank you, I'm flattered. Okay, I'm not sure what more to show here. But, oh yeah, I know what I wanted to show. So this is also interesting, and this is an idea that CrowXC gave me in the Discord recently. So, quick reminder about what an analemma is. So, you probably heard, most of you probably heard about analemmas. So basically, if you take a photo of the sun every day at the same time throughout a year, it will make a figure, something like a figure 8, something like this, and this, something similar to this. So basically in the summer, well, this is from the point of view of the northern hemisphere. I'm in the northern hemisphere, so I'm partial to it. So I basically, by reflex, do everything as it looks from the northern hemisphere. So in the summer in the northern hemisphere, you will get this top of the figure 8. So the sun will be the highest above the horizon. Let's say this is taken at noon, at 12. Wait, this is 12 p.m. or 12 a.m. 12 p.m. I think it's called. 12 a.m. is midnight, right? Anyway, at 12 o'clock at noon, we take the photo every day, and so we in the summer we get the sun very high above the horizon. In the winter it's very low, and in the meantime it's everywhere in between. But it also oscillates to the east and to the west. And that shape is known as the analemma, and it's basically due to two things, and one of the things is the tilt of the Earth's axis, and the second thing is the ellipticity of the Earth's orbit around the Sun. So, if we think about it, when we have the Sun here in the center, and let's say we are here on Earth, and we're looking here at noon. So when we move, again we would again at noon a day later, we would expect to be looking again directly at the sun. But the problem is the speed. Well, one rotation of the Earth around the axis is not 24 hours, right? So after 23 hours 56 minutes 4 seconds, the Earth is pointing in exactly the same direction. So if we looked at the sun here, we would look in a parallel direction here, and the additional 4 minutes are required to rotate back towards the sun. And this is related to the angle the Earth covers during one day, right? So during 24 hours we move by some angle along the orbit, and we need to rotate by this angle as well to point again directly at the sun. But since the orbit is elliptical, this angle covered by the Earth is sometimes larger and sometimes smaller. So near the perihelion, which is in January, so it's in northern winter, we cover a larger angle, and so it takes more time for Earth to rotate to look back again at the sun. And in the summer we are farther away, and so we cover a smaller angle, and so it takes less time for the Earth to rotate back to look at the sun, which means that the solar day is larger than 24 hours here, and it's smaller. And it's smaller than 24 hours here. If we on the equator, if we take only this into account. No, wait. Okay, no. If we didn't take into account the tilt, if there was no tilt, then this would be true. But then there is also tilt, and it's a bit harder to explain how tilt plays into this, so it's actually easier to show this on the celestial sphere. So if we look at the path, maybe I'm not sure how. Okay, I'll try to draw it. So if we look at the path of the sun across the celestial sphere, so if we imagine the celestial sphere, and these are the poles, so the path of the sun throughout the year is something like this, right? It's tilted, because it's actually the Earth's axis that is tilted relative to the plane of the orbit, but we are looking from this geocentric point of view, so we can say that the path of the sun across the sky is tilted relative to the celestial equator, basically. But that means that even if the path of even if the orbit of the Earth was perfectly circular, so we would imagine this. So the velocity at which sun moves along the celestial sphere is basically due to how fast Earth moves in the orbit around the sun. So in the first approximation, where we approximate the orbit as a circle and we say that this velocity is constant, the sun is moving at a constant speed across the ecliptic, on the celestial sphere. But since we are rotating around this axis, this means, let's say that, so to speak, this celestial sphere is a non-inertial reference frame. So it's also rotating at 1 per at 1 per 24 hours this direction. So if the sun keeps a constant speed, then the projection of this velocity of the sun on the equator here will be smaller than here. And it's kind of hard to explain what I'm trying to say. But okay, if we imagine that we are looking... okay, so let's say, maybe like this. If we... so by taking a photo every 24 hours, we're basically trying to slowly rotate across the sky at the speed of once per year. So it's as if we're trying to follow the sun, as the sun will make one lap on the ecliptic during 1 year, but we're also trying to rotate around this axis at the speed of once per year, right? So we have a speed, so basically if we are changing our view at the speed of once per year here, at this point we are going faster than the sun, because the sun has roughly the speed of once per year as well, except it's projected onto the equator at this point. But at this point we are moving actually slower than the sun, because if we are making one rotation per year with the celestial sphere, then this speed at this point is actually decreased because it's like a higher latitude. It's really hard to explain. I hope I'm making sense. But basically, because we are looking at an angle, the points of the celestial sphere, if we try to rotate it at the speed of once per year, the speed here is smaller than the speed here. It's exactly like with the Earth, where the points of the surface have lower speed at higher latitudes. And so if the sun kept the constant speed, here it would actually be larger than the speed of our rotation. So basically, the sun would be overtaking us near the solstices, and it would be going slower than our view near the equator. So now, if we think what it looks like if we try, if we look from this perspective, then it means that, okay, here and here the sun is going this way because it's going faster than we are rotating with it, and here in the middle it is going this way, and so this gives rise to this figure 8. And now this gets combined with the fact that the Earth is moving somewhat slower in orbit here, so the speed of the sun across the sky is a bit less here, and the speed of the sun across the sky is a bit more here, because here we are near the perihelion and we are moving faster on orbit, and this is what gives rise to the asymmetry of this figure 8. So that is basically how the analemma gets created, but this is something we can actually simulate in my simulator, in this simulator, because we can pretend that this rotation of our reference frame is the rotation of once per year. It's as if we were following the celestial sphere at the speed of once per year, and we can put an object in an orbit that will be orbiting the Earth at exactly the same speed. So for example, if we do it like this, if we add a free object over the equator for now, velocity east, and now I need to calculate this. I made this calculation before, but okay, let me quickly make a calculation, and this is 2 pi divided by 86164. So basically this is GM of the Earth, and the omega, well, W, it's kind of similar to Greek omega, so I use W here, is the angular speed of the Earth. And so now I want to find out what the altitude has to be for the orbit to be for the orbital period to be this, And so this can be figured out from Kepler's third law, for example, or I can use that omega. Okay, so I need omega squared, divide gm by this, and this will be the cube of the this is the cube of the semi-major axis, and so okay, this is the semi-major axis, and I also need the Earth. So this is the altitude I need for the orbit, so 35793,140. So 35793,140, and I actually leave the velocity at 0 because this velocity is relative to the rotating frame of reference. So if we look at this, we have an object hovering right above the equator, and if we start the simulation, then it is just hovering right above the equator. Okay, that velocity changes a bit because I'm not that precise. But if we switch to the inertial reference frame, we can see that it's actually orbiting the Earth. Only it's orbiting it at almost exactly the same speed as the Earth rotates. So if we go back to the non-inertial frame, we can see that it seems to be hovering above this. And if we draw the forces, we have the centrifugal force precisely balancing the gravity in the non-inertial frame, and in the inertial frame we don't have the centrifugal force, and so we only have gravity that is the centripetal force, so that is curving the path of the object towards the Earth. So that is what is known as the geostationary orbit. And so here we don't really get any analemma, right? It's just hovering in a single spot above the equator, and that's it. So that's how some satellites work, like TV satellites and things like this. Some telecommunication satellites, they hover above a single spot above the equator because they are in a geostationary orbit. So now we can do something else. We can make this orbit inclined. So we will still have a circular geosynchronous orbit. So the period will still be 24 hours, but it will be inclined, and we will incline it at 23.45 degrees. But now we need to add some velocity east, because at this latitude we are closer to the axis of rotation, so our speed to the east stemming from just the rotation isn't quite enough. So we need to calculate. Let's call this A, and we need to calculate this times the angular velocity times cosine of the latitude. Okay. Wait. Right, and I need to subtract this from the total velocity. So I need this minus. Okay, so this is the velocity I need to the east, 253.94. So if I do 253.94 meters per second, then we're starting north of the equator, and now if we look at this, it starts going to the east, but then turns to the south, crosses the equator. I actually will increase the time step because it makes no sense to wait so much, and then goes to the south, and then starts going to the east again and gets deflected and returns. And so we get
such a figure 8. And so we get a symmetrical figure 8 this time, because this is still a circular orbit, so the speed along the orbit is constantly the same. If we look from the inertial reference frame, it's just a circular orbit that is inclined at 23.45 degrees. It's just a regular circle. But if we look from the non-inertial frame of reference, it makes this figure 8, because sometimes we rotate faster than it and sometimes we rotate slower than it. Real Cygnus writes, so super chat worthy, thanks. Okay, so that is if the orbit is circular. Now we can make it elliptical, and making it elliptical takes a bit more math. So basically, for now we will want the point at the Tropic of Cancer to be the slowest point of the orbit, and so the aphelion. So let's do the calculations. So first things first, eccentricity of the Earth's orbit is 0.0167 approximately. So now the semi-minor axis of the orbit, semi-major axis remains the same, because semi-major axis is what controls the period of the orbit, and we want the period to still be equal to the day. So we can't change the semi-major axis. This is Kepler's third law. So because of this law, we don't change the semi-major axis. It needs to remain the same. We only need to calculate the semi-minor axis, and this is semi-major axis times 1 minus eccentricity squared and square root of that. So that is the semi-minor axis. Okay. Now, so it's this. Okay. Right. So now there is Kepler's second law, and I'll need to draw what I mean. So the thing is, so orbit looks a bit like this. Here is the central object, and the ellipse is somewhat like this. Okay, it's not really perfect, but it will do. So Kepler's second law states that the object, when orbiting, it will cover the same area along the orbit at each point at the orbit. So basically here, in the same amount of time, it will cover this area, so it will cover that same area at this point, right? And this can actually be used to calculate the velocity based on the distance, because the total area of the ellipse, the total area is just pi times semi-major axis times semi-minor axis. So the speed, I will write it like this for lack of a better notation, so the speed with which we cover the area is basically the total area divided by the period, and it's constant due to Kepler's second law. So we know that it's this, but this speed can also be expressed if we look, for example, here, and here is the velocity. It can also be expressed as the distance here times velocity and times the sine of this angle, or the sine of this angle. So this angle is actually 90 degrees, both at the closest and at the farthest point. So we can use this to know what the velocity is, because we know that this is constant, so we know that like this is like v, let's call it v minus, let's call this v plus, let's call this p for pericenter, and this I would call it a, except this is already a semi-major axis, so I don't know, let's call it x. And now we know that v minus times x is equal to v plus times p. Oh, actually this is the product of velocity, radius, this angle, and divided by 2, because this is basically the area of a very small triangle. So if we think that this is v times dt, then the area of this triangle is v times dt times r times sine of this angle divided by 2.
And so if we go for very small dt, this will actually be pretty much like a part of the ellipse, and this will be the area covered in time dt. So this is basically v times r times sine of that angle divided by 2. And so we know that this is 2 pi ab divided by the period. And one more thing, p is actually a times 1 minus eccentricity, and the x is a times 1 plus eccentricity. And now we have everything we need to calculate the speeds at the fastest and slowest point. So we are interested in the slowest point. So we need this distance, and we need the speed, which will be basically 2 pi ab divided by t divided by this. So we can calculate that, and this 2 times pi times a times b divided by t, which is 86164, I will just call L. And if I divide it by a and by 1 plus eccentricity, we'll get that this is the v we need. But this is in the inertial frame. So to calculate it in the non-inertial frame, we also need the distance. And the distance is a times 1 plus e. So this is the, wait, what? Oh yeah, eccentricity. E is actually Euler's constant 2.71 something. So yeah. Okay, so we need this, and now the velocity relative to the reference frame will be v minus x times angular speed times cosine radians 23.45. So it will be like 155.9 meters per second, and x minus r is the altitude. So we can just use these numbers to get an elliptical orbit that will be geosynchronous and that will have its farthest point at the Tropic of Cancer. So 3649781. 364978281, and the velocity was, I don't remember, 155.9. Okay, so we start from there, and if we do this, we should get an asymmetrical figure 8, because the object will be the slowest at the highest point and the fastest at the lowest point, so it should be fatter at the bottom than at the top. And we'll see. If I didn't make any mistakes, this should kind of resemble the solar analemma already. And we can see that indeed we got a figure 8 that is fatter at the bottom than at the top. So this is the asymmetry that we get from the ellipticity. And again, if we switch to the inertial reference frame, this is just a regular orbit, and you can barely see that it's elliptical actually, because this is very, very close to a circle still. But it's slightly non-circular. Only it's hard to see. But it's very visible in the non-inertial reference frame because we have this asymmetry here. So the next stage would be to try to skew this analemma, and I actually tried doing that recently, but it's a lot of math, because basically now we need to kind of rotate this orbit so that the point above the Tropic of because right now what we did is the Tropic of Cancer is here, right? So at this point the object is above the Tropic of Cancer. So what we want to do is the object to be at the above the Tropic of Cancer, not at this point, but let's say at this point.
because actually the Earth is not at the aphelion when we have the summer solstice, when we have the June solstice. The aphelion is like a week later, so we are actually slightly before that, and so we would need this point to be above above the Tropic of Cancer. So we would need to rewind a bit, and we would need to calculate what is the distance here and what is the velocity here. But here we would need two components. There is the tangential velocity, which would be to the east in our case, and we would have some outward component as well, which would be upwards in the terminology of the simulator. So this all can be calculated, and it's not that okay. Let me check if anyone's watching and if anyone wants to see me try to do this, because it is a bit it is a bit of work. But if someone from the ones watching wants to see, if someone from the viewers wants to see it, I can try to do this calculation. But I don't know if anyone's interested. And it's getting late, at least for me. Okay, Real Cygnus says hell yeah. Okay, let's try then. So, the important bit. The important bit about an ellipse. So if we have the central body like here, and the ellipse looks something like here, then when we have like an angle phi here, and we want to calculate the distance of this point of the ellipse from the center, then there is a simple equation which says that r of phi is L, and this L is actually this this is called semi-latus rectum or something like that, and it's this segment here, L divided by 1 plus eccentricity times cosine of phi. So that's the equation. So basically what we really want is to find, knowing this angle, and this angle we will actually know from a parameter which is called the argument of perihelion. So this so astronomers, when describing orbits, they are using a few numbers to describe what is the shape of the orbit and how exactly it is oriented in space. So for example, if we have some plane of reference and we have the central body and the orbit looks something like that, then then the point at which this plane is crossed by the orbit is called the ascending node. Well, there are two nodes. There is ascending node and there is descending node. So when the body goes from below the plane to above the plane with some definition of above and below, because of course in space there is no objective above and below, but we say that there is some above and there is some below, and so when the object goes from below to above, then it is the ascending node. When it goes the other way, it is the descending node. And then the angle within this plane between the ascending node and the closest point is called the argument of pericenter. And from here we can basically get how the orbit is oriented. So for the Earth, if we check, do I still have this open? Earth orbit. I think if we just go to Wikipedia, then we will find out that we have longitude of ascending node and we have argument of perihelion. And this argument is 114.20783 degrees. So it means that
Yeah, that makes sense. Okay, so it means that after we cross the ascending node, then basically this angle will be 114 degrees. And now you might ask, what is the where is the ascending node in the Earth's orbit and what is it relative to? So basically the plane of reference used in astronomy is usually the plane of the ecliptic. And for the plane of the ecliptic, and the Earth's orbit is within the plane of the ecliptic. If we look at the wiki, I think the inclination, because the inclination is the angle between the plane of the orbit and the reference plane. So if we look, it should say that the inclination is, yeah, okay, it's almost 0 to J2000 ecliptic. Okay, it's a bit more complicated because basically the plane of ecliptic also changes, so you need to define when exactly it's defined, etc., etc. So it becomes a bit complex, but to the ecliptic is pretty much 0. So for all intents and purposes, it's 0. And the ascending node, does it say anything? Okay, it's minus 11 degrees to J2000 ecliptic. Huh. This might explain why I got the bad result. Okay. So this basically says that we have minus 11.26 degrees to the ascending node. So okay, let me show you. Okay, so basically it means that if we have some reference direction, then from this reference direction to the ascending node, we need to go back by 11 degrees, and then we need to go from here along the plane by 114 degrees to get to the perihelion. And I was kind of, but yeah, this doesn't really concern us. I was just wondering if it's important, but okay, yeah, it's not that important. So basically what we really want is so we want the plane of the orbit to be rotated in such a way that we have 114 degrees from the point where it intersects the equator to the point that we have the pericenter. So right now we have it like this. Here is the tropic. At this point in the orbit we have Tropic of Cancer. These are the nodes, because this is where the equatorial plane will intersect our orbit, and so we want the pericenter to be so. So this is no wait. Okay, so let's just say that this is the ascending node. So we had it at 90 degrees, and we want to have it at 114 degrees. So we need to rotate the plane by a further 24 degrees. Does it make sense? Yeah, it does make sense. Okay, so if we rotate it by 24 degrees, this will mean that here is the angle of 24 degrees, and we are in this should then be at about this point should be above the Tropic of Cancer. So if we take this whole ellipse and rotate it by 24 degrees, this basically the axis of the coordinate system now will intersect it here, 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 and here, right? And then the angle between this will be the ascending node, and then the angle between this and this will be 114 degrees, and so we are interested in this point 24 degrees before the apogee in this case, because this will be an orbit around the Earth, right? So this is perigee and apogee on our orbit. Okay, so this angle, this phi we are interested in now, is 180 minus 24, which is 156 degrees. So now we need to calculate L, but L is easily calculated because basically we know that the perigee is semi-major axis times 1 minus eccentricity, and at the same time it's L divided by 1 plus eccentricity. So we will get that L is equal P times 1 plus eccentricity, or it is equal A times 1 minus eccentricity squared. So let's calculate it. So L is A times 1 minus eccentricity squared. So we have this. And now we need to calculate our distance from the center at 156 degrees. So this will be L divided by 1 plus eccentricity times cosine of radians of 156. Yep. So this is our distance. Now, tangential velocity we can calculate easily because we can just use what I already did before. I can just take the big L, which was just a reminder, the big L was this. So I can take big L and divide it by the distance, and I will get basically the tangential, the velocity to the east. So if I do this, so this will be velocity to the east. And I can decrease it by times x times cosine of 3, 4, 5. Okay, and this is something I will have to input into the simulator as the velocity to the east, but we also need the velocity outwards to up. So VE2, let's just save this. And to calculate the velocity outwards, we will use the conservation of energy. So basically the total energy in an orbit, if I write here it will be fine, okay, is v squared divided by 2 minus gm divided by r, divided by the distance. And this is constant because of conservation of energy. We can divide it by m, and we have this is also constant because the m doesn't matter. So we can just let's just call this E, and don't and just disregard the mass, and we'll just call this E. Okay. This is constant, and it is actually equal to minus gm divided by 2a, so 2 times semi-major axis. So we can use this to calculate the total velocity. So we will just move this to the other side, and we will say that gm divided by r minus gm divided by 2a is equal v squared divided by 2. So v is just square root of 2gm divided by r minus gm divided by a. And this way we can calculate the total velocity at this point. So v will be 2 times gm divided by x, so x is our distance, minus gm divided by a, and square root of that. So that is the total velocity, and as we can see, the total velocity is only a fraction different from the velocity, from the tangential velocity. So now to calculate the outward velocity, we can just use the Pythagorean theorem, because this is our v, this is our VE, and this will be our VU, let's say V up. So we have that V squared equals VE squared plus VU squared. And we want to calculate this, and we have both this and this. So we will do that, and we will say that VU is V times V minus VE times VE square root, and VU comes down to about 21 meters per second. And so we have everything. We only need x minus r so that we know the altitude, and so this is the altitude, this is the velocity to the east, and this is the velocity upwards, and we should be fine. So let's try to enter this into the simulator. 36434429. Okay, what's the velocity here? It's 164.6, let's say. And up it was 21. 20.9, let's say. Okay, and this should give us an elliptical orbit that is rotated by these 24 degrees. But when I ran it yesterday, it was really hard to see that it actually worked. But we can try to see if we see anything differently. The orbital mechanics 101 I never had, yeah. Yeah, it's actually a very interesting piece of math and physics. Okay, and what we see also looks pretty much symmetrical. It's really hard to see if it's different. It should be. So now we should have this point, well, the farthest point should be somewhere here, actually. Well, but it's too little of a difference, I think, to see if it's not symmetrical anymore. So yeah, so it's a bit underwhelming, unfortunately. I think that what also makes it a bit problematic is that if we look from the side, well, this is actually curved, right? It's not a flat analemma. We get this figure 8 that is actually on the surface of a, well, roughly sphere. So this might also introduce a bit of a distortion here, and we might not see the asymmetry as well as we should be seeing. Yeah, but we can just try this calculation with some larger angle to see if we get something different. So let's try. So what would be, let's try rotating it by 90 degrees and see what happens. Okay, this was a bit silly because then x is just equal to L. And okay, so V east is L divided by x, VE2 is VE minus W times x times cosine of radians 23.45. So let's see VE, VE2. Okay. And what now? Total V is equal to times Gm divided by x minus Gm divided by a square root. Vu is equal V times V minus VE times VE 0.5. And let's see, Vu is now 51 meters per second. And x is this, x minus r. Okay, so let's try entering this 35781,380. Did I remember this correctly? Yes. And V east is 255.2. And velocity up was something like 51.4, let's say 51.4. Okay, so let's try this. And okay, so this should basically make it so that the perigee and apogee are above the equator. So I rotated it should have rotated the plane of the orbit by 90 degrees if I did it correctly. And this should introduce more asymmetry to the figure 8. We'll see what happens. I'm really not sure what this will look like. Okay, yeah, not quite what I expected. I think it's a bit different. but not quite as different as I would have thought. It seems just at a glance that now the upper part is a bit fatter than the lower part, and that it's a bit skewed to the side, as in it's not perfectly vertical, but it's a bit skewed to the right. But that might just be me. I'm not, yeah, it is. If you compare it with the grid behind it, you can see that the slope here is more steep than the slope here. So it is a bit skewed to the side. But the effect is so slight that it's very hard to see. So we won't see this beautiful asymmetry of the analemma that we saw, that we can see in the true analemma. Oh, I can see we have Jose and we have Truth Nerds. Hi. Yeah, Jose says no need to answer me that. No, no worries. I mean, I'm getting. You got the more hardcore part of the stream. Okay. Yeah, so that's basically what I had for you today. I don't think I really have much more. We tried with the analemma, so it's possible to see something. It's hard to see it as it's hard to make it as asymmetrical as we would like to. I tried actually, let me try to show it to you maybe. So I tried yesterday to make a screenshot of the analemma that was supposed to be asymmetrical. Okay, so that's the analemma that was supposed to be like the Earth analemma. So if we do this and we scale the image and we just try to squeeze it a bit vertically, so it's 659, let's do it 150. And I don't know. Yeah, it's maybe slightly asymmetrical, but it's the effect is very, very slight. Wait, no. Cancel. Maybe if you squint, it's slightly skewed the way the analemma is supposed to be, but it's a really slight effect. Dora writes, this is wonderful modeling, a bit understatement, hard to follow someone that is out of touch with math. Yeah, I get it, but interesting to see how you attack the problem. Well, thanks for the compliment, and yeah, thanks for watching, of course. Okay. So yeah, I don't know. It's really all I had prepared for today. So unless someone wants to say something, add something, or unless someone has some request, I think we'll be finishing. I'm already talking for over 3 hours, so it's a bit long. But hopefully this was at least a bit useful. It would be great if I think I might make parts of what I was talking about today into some videos, because I think it could be useful for discussions about reference frames and Coriolis and stuff with people that don't really know what this is. But then again, maybe not, because nothing really helps in discussions with people like that, mostly. Well, it might help with people that actually want to learn, which unfortunately most flat earthers don't fall into that category. Okay. Okay, I see. And Truth Nerds, it's very simple math. I'm not helping, am I? Yeah. It depends who you ask. it's simple relative to some stuff that is being used in physics. It's probably not simple to someone who isn't really in this stuff. Who I don't know. For people who didn't study physics or maths, it might be. I get that it might be a bit overwhelming. You don't really deal with such stuff in everyday life, so if you aren't really used to like solving problems in physics and things like this, then this might be overwhelming. Oh, Real Cygnus says much thanks. Thanks to you as well. Thanks to everyone who is watching, that I'm not talking to myself. It's always nice to see that someone is interested. Alright, yeah, so I think we'll be finishing. Unless, as I said, unless there is anyone interested in coming online, we can open a voice chat in Discord and try having a chat if someone wants to come on. But otherwise, I think we'll be just finishing. Dora says, I studied physics and dropped out, but that was many months ago. Forgot just about everything. Yeah, if you're not... you can forget stuff. I also forgot a lot of stuff from my studies. There are areas in physics I wouldn't touch right away. I would have to really get a refresher on a lot of stuff, because I'm also like not dealing with this stuff every day. And Jasper E says, this or that way you need to keep this live up. I'm not sure what you mean, as in to keep talking so that the live goes on, or to keep it up as in available on the internet. And I really hope that it's the second one, because I don't really have much strength in me to keep it up as in keeping it going. Okay, yeah, I think we'll end at this. So yeah, again, thanks to everyone watching, and yeah, if you're interested in playing with this simulator for yourself, it's available, so the link is already in the pinned comment under my last video, but I will also put it in the description of this live, so that you can check the source code, you can download the compiled versions, and you can play with it. Oh, hey, Jasper says the second one. Okay, that's good. That's that's a relief. Okay. Alright. Yeah, so thank you to everyone who's still with me, and thank you to everyone who... Well, okay, yeah, I see one more question from Real Cygnus. Should be able to build a Windows exe easy. I uploaded a Windows exe in the releases tab on GitHub. You can find a compiled binary, but building it is basically a matter of downloading the Rust compiler and then typing a single command. It's cargo build -- release. So if you really want to compile it yourself, it's really simple, because the Rust toolchain is really easy to use, but you don't have to. There is a binary compiled already. Okay, great. So yeah, so again, thanks to everyone watching, and yeah, see you on the next video or live or whatever. There will be some materials for sure. So yeah, thanks and goodbye.